points in the class. The total points in the class are curved at 88. I already updated. A curve meaning I'm just going to make it a little easier to get an A, 88%, 78%, but the C is fixed at 65. That doesn't change because that's already a wide C range. A lot of people keep their C range at 70%. Okay. And so the chances are 0 I'm going to curve the test because you guys should be looking at your total points cumulative, not just one exam score. Basically, and that brings us to the homework because some people think, okay, I'm doing okay on the test, but not neglecting their homework, and the homework is a lot of points. So some people are failing because they haven't turned in any homework in, and so that's why I gave a grace period for that first assignment. You could just turn it in, chapters 1 through 4, up until the end of the semester, and recoup those points. That's 40 points worth. What's that?
What's the total point?
Of homework? The total points?
Not the homework, but your times.
I don't know, just add it up. Off the top of my head, it'll take me a couple of minutes, but you mean the total points in the course is on the syllabus, about 1,000 points, right? Roughly.
Was this test out of 100? The test we just took?
This test that we just took is out of 100, right? So 10% of your score. All right. Anyway, there are, at UCLA this happens quite a lot because at UCLA they get one midterm and one final. And so what happens is, for some reason or other, the people blow it on the midterm. It's like halfway in the quarter, 5 weeks. They blow it on the midterm, and then they can pull out on the final because the final is worth a lot more as far as percentage goes. Your final is worth 200 points, so 20% of your grade. And so that happens. But we have more than one midterm. We have multiple. All right, if there are no other questions, are there any other questions in this stuff? Since I'm behind schedule, I want to just get moving to get caught up with Chapter 7 stuff. So we're talking about work. We're looking at one reaction here. This work stuff conceptually is difficult, so that's, some people, they're expecting the test to be easy, but, I was thinking it'd be easier without dealing with this, which conceptually throws a lot of people off. How do we factor in work and what do all these symbols mean? So
It's not difficult, but it's working for us.
So if we look at this reaction, CH4 plus 2 O2s, these are gases. This goes to CO2 gas plus 2 H2O liquid. Here. What is important is there are different ways that we can burn this. This is just combustion of methane, right? What are the ways we can burn methane? We can burn it at constant pressure or constant volume. Well, it turns out, are we going to get the same amount of energy? Yes, we're going to get the same amount of internal energy change. The internal energy change is always the same. Now, this is fixed no matter how you burn it. But what's not fixed is Q and W. This is fixed because this is called a state function. Q and W are not fixed. These are not state functions. So the amount of heat and the amount of work is going to vary depending on how we do this. Now I asked you, if we burn this in a bomb, if we burn this in a bomb, that is, okay, let's burn it in a bomb. Is the reaction going to do any work inside a bomb? No. And so the reaction does no work inside the bomb, and so all that energy is converted into heat. Versus if we did this reaction under conditions of constant pressure, this is a constant volume. Then what's going to happen? Well, we have to look at the volume change. So for example, what is the initial volume here, roughly? And so let's just estimate the volume. We have 1 mole of methane, 2 moles of O2, so altogether we have 3 moles of gas. An ideal gas occupies how much space at 1 atm and 298 Kelvin?
24.5 liters.
Yeah, 24.5 liters, so we're just rounded to 25. So we rounded to 25, we got about 75 liters at the start. After the reaction's over, is there any methane in O2 left? No, it's completely consumed and replaced by 1 liter of CO2 and 2 moles of, or not 1 liter, 1 mole of CO2 and 2 moles of water. And so that's 3 moles. But it's not 3 moles of gas. What is it?
1 mole of gas, 2 moles of liquid.
Yeah, 1 mole of gas. 1 mole of gas is going to be about 25 liters. And
2 moles of water.
2 moles of liquid water. Now, 2 moles of liquid water has what volume? 36 milliliters. And so we're going from 75 liters to about 25,036. You know, this is just approximate. And so what happened to the volume? Shrank, right? Now, when the system's volume had to shrink. When you're blowing up a balloon, that requires work. But when a balloon deflates, you pop it or put a pinhole in it, and it deflates. Do you have to do work to deflate the balloon? Like do you physically squeeze? Like here, you have to squeeze it because of the walls. But for a balloon, would you have to squeeze the air out of it? No. Who squeezes the air out of it? The surroundings. You know, we live in one atmosphere of air, and so the surroundings does the work here. And so what we have here is we have a delta V situation. You know, delta V here is the volume strength. The delta V is actually less than 0. And so if we recall, the work of the system is equal to what? The work of the system is equal to minus P external delta V of the system. And so we look at delta V of the system. Delta V of the system, well, the work of the system is going to come out. Delta V of the system is negative. This is positive. That means the work of the system is greater than 0. If the work of the system is greater than 0, then what does that mean? That means the system gained energy by having the surroundings do the work. And so in other words, we interpret this as this. Surroundings does work on the system. The surroundings squeeze the volume down, or pinch it down. Surroundings does work. System gains energy. And so we know that,
Is that system doesn't work, so you lose your energy and then the system gains it? The system gains energy?
System did not do work. System didn't do any
No,
work.
surrounding doesn't work.
Surrounding
So
does work.
surrounding lose energy, so
Yeah.
system gains energy?
Yes, right, because energy is neither created nor destroyed. And so that energy has to go somewhere, in other words. And so we have delta U is equal to Q plus W. So we think about this. Now, the work, the system gains energy by having the surroundings do work. And so the system gains energy initially. And that means that after this, the system is going to lose energy in the form of, actually this all happens at once, but lose energy in the form of heat. So now we're going to start labeling this. You know, this is Q sub V. This is the heat released under constant volume conditions. We call this Q sub P, meaning the heat released under constant pressure conditions. Now, is the heat released under constant volume and the heat released under constant pressure the same? No, they aren't the same. Which one's bigger? For this reaction.
Heat under constant volume.
Which one's bigger? The heat under constant volume conditions or the heat under constant pressure conditions?
Constant volume.
Which one is going to release more energy to the surroundings? Constant pressure conditions or constant pressure? So we say that the heat under constant pressure conditions is bigger. If you were heating up a cup of coffee, which one is going to provide more heat to heat up the cup of coffee? Constant pressure. So the heat released under constant pressure conditions is bigger than the heat released under constant volume. So, in other words, QV is smaller than QP. Little asterisk here. Because you cannot think of this in terms of magnitude. Do not think of energy in terms of the number line. Like Petrucci does, like the book does. I'm going to deviate from our book. Although, you know, Petrucci goes into a little explanation about what he means by this. Let's talk about this now. For example, what is a bigger number, right? 10 or minus 10? Some people will say 10 is a bigger number, right, than minus 10. In other words, 10 is a higher temperature than minus 10, right? Bigger number. Some people, to me, this is the same. It's the same because it's the same amount of energy. It's just being exchanged one way or the other. This is like a $10 bill. Which is bigger? A $10 bill leaving the system or a $10 bill coming into the system? They're the same, right? Well, Petrucci does this. Petrucci says, well, this is a more positive number, therefore this is a bigger number than this. Does that make sense? It doesn't make sense in terms of energy. And so ignore the answers in some where he says which is bigger, you know, because Petrucci is going to say this is bigger, right? But when I think about it, oh, $10 bill, $10 bill, the negative is irrelevant, right? Okay. And so for me, yeah, QP is bigger. QP is going to release more energy to the surroundings. So if my surroundings is a cup of coffee, then I'm going to get more heat. Does that make sense? And so what we're going to do is we're going to look at different scenarios. We'll look at one more scenario and then we'll look at some generic ones. Okay, the next example is this. I could do this in a bomb, or I could do this under constant pressure. I should just say constant volume. The bomb is there for visual
visualizing this. So I take 50 mils of HCl plus 50 mils of NaOH. And so what's my V initial? 100 mils. And then I end up with 100 mils of NaCl solution. This is solution. So if I did this in a bomb, well, you know, I know that delta U is equal to Q plus W. In a bomb, can we have any work done, really? No. No chance for any work done. So that's zero. So all the heat, so this is called QV, right? Versus if I did this under constant pressure, we could have work done. Under constant pressure, we do the same thing, right? Delta U is equal to QP, right, under constant pressure, plus W. But what is delta V in this case? Under constant pressure conditions, delta V is equal to, well, we started off with 100 mils, we end up with 100 mils, delta V is 0 under constant pressure conditions. If there's no change in the volume, and we aren't hooking this up into any electricity generator or anything like that, is there any work done? Is it lifting some mechanical weight? I mean, no, and so the work is 0. And so for this particular reaction, QV is equal to QP. Now this is where people get all screwed up, because there's some people, they like to think in, you know, absolute. You know, they want to know QP. They always ask me, QP is always greater than QV, right? You know, they want one thing to memorize. Is there one thing to memorize? No, you have to take this case by case. Because sometimes QP is greater than QV, sometimes QP and QV are the same, and sometimes QV is greater than QP. Does that make sense?
Could you explain what time under constant pressure the work is larger?
Because under constant, if we mix this under constant pressure, I have 50 milliliters of HCl solution plus 50 milliliters of NaOH solution. What's that going to make? It's going to make the same thing, 100 milliliters, no matter if it's at constant pressure or constant volume. It's going to be the same thing. And so if I seal this up in a bomb, there's no pressure generated. The bomb, what the bomb does is it keeps the volume constant, fixed. And therefore, if the reaction generates gas, that pressure is going to increase, but the volume is going to be contained, right? If the volume consumes gas, like the previous reaction, then we aren't going to have an implosion because the bomb is going to keep the volume fixed. Whereas in constant pressure, we don't have a bomb keeping the volume fixed, but we don't need a bomb. Do you need to do this reaction in a bomb? No. Are you going to worry about a pressure explosion or a pressure implosion by mixing two 50 milliliter liquids? No. And therefore there's no change in volume. We don't have to worry about it at all. And so going back to this, then this is the way you can visualize these different scenarios here. And so first let's look at exothermic reactions. For exothermic reactions, we're looking at the systems like your energy generator. You're getting energy from the system, let's say. Right. And so delta U is equal to Q plus W. Now, the work, are we getting any useful work from this? Basically, if you burn methane, the work is kind of unavoidable work. This is called the natural work of a chemical reaction that we're looking at. And so P delta V work is the natural work of a chemical reaction done under constant pressure conditions. In other words, you can't avoid this. If you want to maintain constant pressure, right, you can't avoid this for some reactions. You can't say, I don't want to do that work. I don't want to have the reaction do that work. It's not possible. If a gas is generated, the system's got to expand, otherwise pressure's got to build. Or if a gas is consumed, the system's got to contract, otherwise pressure decreases. And so one way of thinking about this then is like this. We're kind of interested in how much heat we're going to get, or how much energy, we're going to get released into the surroundings here. And so Q is going to equal delta U minus W here. And so if that work is unavoidable, then it's kind of like a tax. And so the way we think, or the way I think about this is the gross pay. And so let's say we're dealing with an exothermic reaction. We should get 3,000 kilojoules. We should get 3,000 kilojoules from this reaction because that's what the reaction has in terms of gross energy. But the work might mean that we don't get it. For example, if the system volume has to expand, then it's a tax. This is for exothermic reactions. Exothermic reactions in which we're trying to get energy from the system. If delta V of the system grows, then the system has to do work, meaning some of that 3,000 kilojoules we're expecting, it's going to be a little less because the volume had to expand and that costs energy. Or it's zero, if delta V of the system is equal to zero, we don't have to do any work. We just get what we expect. Or it's a bonus if delta V of the system shrinks. We just saw that. In the methane combustion, we get a little bonus heat from the surroundings doing work. And so what we get is this is your net after tax or after bonus pay. Net pay off to the surroundings. Does that make sense? So it depends on how we burn the methane, right? Depends on how we burn the methane. Otherwise, the heat is not a state function. This could be QP or QB. And so what we want to do is we want to get the same net pay each time we do the reaction. How would you do that? Because if somebody says, well, how much heat am I going to get from the combustion of 1 mole of methane? What would you tell them? Well, it depends. Are you burning it on a bomb? Are you burning it in the oven lab? What's the pressure? It becomes a hassle because the amount of heat you're going to get from burning 1 mole of methane varies.
So you could give them an answer, well, it varies. But, that's not such a great answer, is it? If somebody asks you a question, you want to give them an answer. So what would you, well, the answer that we need to, we got too many unknowns, right? Too many unknowns. And so what do you do when you have too many unknowns? Well, you could say, oh, I can't solve it because there are too many unknowns and I don't know how to solve it, right? Or you could make an assumption. Now, what do you want to assume? Let's assume we're going to do the burning under conditions that most people burn it under. Would that be inside a bomb or outside in an open lab? In an open lab. So assumption one, we're going to say, well, because of this, we can't answer it unless we make some assumption. All right, so the first assumption we're going to make is we're going to do this under constant pressure. It makes no sense to do it under constant volume because how many people have access to a bomb? Practically nobody. Okay, what's the next assumption that you would likely make? Okay, if you're going to pick just one temperature to do the calculation, would you pick 0 degrees C or room temperature? Room temperature, right? It'd be ridiculous to pick 0 degrees C because how often do we burn methane at 0 degrees C? Never, right? And then if you're going to pick a pressure, what pressure would you pick? 1 atmosphere. And so the typical data that, the typical answer that somebody's expecting is first, constant pressure. And then these aren't fixed. Because not everybody does everything, The second would be at 1 atmosphere, and the third would be at 298 Kelvin. But these can change. But if you're going to pick the most common conditions that everybody does it under, then that would be it, wouldn't it? But sometimes you aren't at room temperature. Sometimes the temperature is lower than 298, right? In fact, in the lab, has the temperature ever hit 25? No. And sometimes we're at higher temperatures. If the air conditioning blows out, then we're at higher temperatures. And so the temperature is not rigid. These are not rigid. But these are the most common conditions. And so if somebody asks you about the heat, then automatically you'd make an assumption. Constant pressure, 1 atmosphere, and 298 Kelvin. And then we can answer it, right? All right, so this is what we're going to do. If we fix the conditions, then the amount of heat is always the same. For burning 1 mole of methane. Right? If you burn it this way and somebody else burns it the exact same way, then of course you're going to get the same amount of heat. Does that make sense? So what we do is this. We make Q into a state function we make Q into a state function from a path-dependent function.
by placing restrictions on the path. For example, there are many ways to climb up the mountain, right? But if you restrict it that you always have to climb the mountain this way, then you know everybody's going to have to climb or exert themselves of that much. When we place these restrictions, we no longer want to call it Q. Because Q, we don't know, you know? What is a Q? It could be QP, it could be QV, right? What's the pressure? What's the temperature? We don't know, right? It could be anything.
When you say Q or W, call like the path dependent, it's because it varies, or
It varies, right?
because it varies?
It varies. It varies depending on the path.
So the path is like your temperature and pressure conditions?
Right. It's your conditions that you carry out. It's the path. You know, let's say you're climbing a mountain. The mountain, does the height of the mountain change? Is that variable? The height of the mountain is a state function. That never changes. But, you know, how many miles do you have to hike to the top of the mountain? Is that fixed? That is called a path-dependent function. And so you might hike like this, take lots of switchbacks, make the angle, or somebody might just go straight up. And the person who went straight up is going to take a lot fewer miles than the person who went back and forth, all the way to the top, right? And so the path, that is the length of miles traveled to climb this mountain, is not a state function. But we can make it a state function. How can we make it a state function? Yeah, you block off all these other paths and force everybody to take the same path. And when you force everybody to take the same path, then of course the number of miles traveled will be the same for everybody. When we place these restrictions, not all, they don't have to be. When we place these restrictions in general, then Q becomes a state function. You know, whenever we burn a mole of methane, we're going to get the same amount of heat. And so the definition is this. QP, we place the restriction of constant pressure, we're going to change the symbol to delta H. And so now delta H is always going to be the same for burning a mole of methane, you know, as long as we follow the exact same path, right? If we deviate from this path, are we going to get the same heat as delta H? Let's say delta H required 298 Kelvin and 1 atmosphere, and all of a sudden we're at 10 atmospheres and 350 Kelvin. Is delta H valid? No. Delta H is not valid for those conditions because they were defined for a different set of conditions, right?
What's P stand for?
What does P stand for? Constant pressure. The heat at constant pressure. And so this is what delta H is. Delta H is the heat at constant pressure with certain restrictions. Right? And so let's talk about those restrictions in more detail here. QP is equal to delta H. Actually, it's defined as delta H. I'll use 3 lines here. QP is defined as delta H, right? Delta H is net heat we're getting from delta U minus W. Okay, what are the restrictions we're going to place on this? One of the restrictions is only P delta V work allowed. And so what we end up with is delta H is equal to delta U minus a minus P external delta V of the system. In other words, this is going to equal delta U plus P delta V of the system. And so it's the same thing. You know, delta H is our net. This is our gross. And this, the work, is a tax or bonus. For EXO. And so let's look at some scenarios here for this. First, we're going to look at internal energy diagrams, and then we're going to look at enthalpy diagrams. So let's go to internal energy diagrams here. Internal energy diagrams is plot the internal energy on the y-axis like this. And then we're going to look at 3 exothermic scenarios. And then 3 endothermic scenarios. Okay, what are we going to restrict? We're going to do this under constant pressure. And P delta B work only. These are the restrictions for delta H. It turns out delta H is going to be a function of temperature and pressure, because we didn't fix the temperature. The temperature is not fixed at 298, and the pressure is not fixed at 1 atmosphere. But the most common T and P is 298 K and 1 atmosphere, but T and P can change, or variables. The reason is that people don't want to be forced always, you know, okay, constant pressure, yes, but they don't want to have to be forced to always work at room temperature. Sometimes people want to increase and sometimes people want to decrease the temperature. And the same thing goes for pressures, you know, sometimes they want the pressure to, you know, can you imagine having to, you know, oh, what's the atmospheric pressure today? Oh, it's 750. Uh-oh. I got to pump more air in here to get it to 760. Do you think anybody's going to hassle with that? Or let's say the pressure, oh, 764, shoot. I got to hook up my vacuum to the room to suck air out, right? It's too much hassle. You know, obviously we want a fix, like a reference, like 298 and 760, but, you know, if the pressure's at 750, no big deal. We'll just say constant pressure at 750. Can change things a little bit, but hopefully not too much. All right, so what are the 3 scenarios here? Okay, scenario number 1. Under constant pressure conditions, the volume doesn't change. So V, let's go here. V initial, V final are equal. And so if V initial and V final are equal, under constant pressure conditions, was any work done? No, and so we get this scenario, delta U is equal to Q, right, plus W. W is 0, and therefore delta U equals delta H. All right, the next scenario is, let's say the system had to expand. And so V initials like this, V finals like this. And so what has to happen is, okay, delta U is equal to Q plus W. And when we look at this, well, the system had to do work. You know, V initial smaller than V final, so the system had to blow up the balloon, right? If the system has to blow up the balloon, then some of the energy has to be consumed in the form of work. And so we lose some energy doing work to blow up the balloon. It's called the system. And therefore, are we going to get as much heat released from this? No. And so we know that, you know, QP is equal to delta H, right? And so in this case here, you can see that delta U is bigger or smaller than delta H? Delta U is bigger or smaller than delta H? Delta U is this drop here. Delta U is bigger than delta H. Right? Why? Because we lost some energy doing work. Could we avoid doing that work? No, not unless you do it in a bomb, right? But doing it under constant pressure conditions, you cannot. And so this is why I call it unavoidable, this work. And so is this a tax on the system or a bonus on the system? This is a tax on the system. That means the system is going to release less energy to the surroundings.
Question?
Yeah.
That label should be constant volume.
No, constant pressure. This is like taking 50 milliliters and there's no change in the volume. Like, you know, what we had earlier, 50 plus 50 is 100. So we had 100 milliliters to begin and 100 milliliters final. And so even under constant pressure, the volume didn't change. And so, in other words, here, well, delta U is greater than delta H. Delta U is equal to delta H plus W. Well, what is W? Well, W is, this is equal to delta H plus a minus P external delta V of the system, right? Which means it is going to be, you can figure it out, etc. You can rearrange it if you want. All right, let's look at one more scenario. Exothermic. Let's say the volume shrank. So we started off V initial and V final turns out to be smaller. So we know delta U is equal to Q plus W here. Delta U is the full drop. In this case, you know, V initial is bigger than V final, which means that,
Other way around, right?
yeah, it's the other way around. The surroundings does the work. If the surroundings does the work, then the system gains energy from work done by the surroundings. So the system gains energy by work done by the surroundings. Therefore, the amount of heat that's released is more. And so this will be QP, which is equal to delta H. And so in this scenario, then delta U is greater than, less than delta H. Right? In other words, delta U is equal to delta H plus W. In this case, was W a tax or a bonus? A bonus, because now the surroundings is going to get more energy from this. And so let's say we're supposed to get $3,000, but we ended up getting $3,100 because of $100 of work done by the surroundings. And let's look at endothermic reactions next. Rather than getting paid, now we have to pay the system. We're the surroundings, right? And so endothermic reactions, the system's energy increases. That means the surroundings' energy has to decrease, and we're the surroundings, so that means how much do we have to pay? And so in terms of internal energy diagrams, we're going to look at the three scenarios here for endothermic. Let's say V initial is down here. This is V final here. And this is going to be our delta U here. Delta U is equal to Q plus W. So was there any work done here? This is under constant pressure.
So the volume's the same.
The volume's the same, so under constant pressure conditions, if the volume's the same, there's no change. No work done. So this is 0. This is QP. And therefore, delta U is equal to QP, which is equal to delta H, which means that there was no tax, no bonus, your gross pay and your net pay. So whatever we have to pay is the amount that is required to increase the internal energy of the system. All right, the next scenario is, what did we have? Volume decrease? Yeah, volume decrease. So if we have a volume decrease, here's V initial, here's V final. So V final is less than V initial. Here V initial and V final are the same. Here V initial is greater than V final. And so when we look at this reaction, work was done because the volume changed. Who did the work? Who did the work? The surroundings. The surroundings does the work. So if the surroundings does the work, what happens to the system? The system gains energy because the surrounding. Now I'm gaining down here because this is where we're starting. The system gains energy because the surroundings did the work, and the system benefits from that. And therefore, Q is like this. This is Q here. And so we know that delta U again is equal to Q plus W. We're doing this under constant pressure conditions, so that's QP. And so there's a QP here. And so let's say normally the price for this internal energy change is 3,000 kilojoules. Do we have to pay 3,000 kilojoules? No, actually we only have to pay 2,900 kilojoules because 100 of those kilojoules is coming from the surroundings, so we got a little help from the surroundings. The surroundings helped us. Does that make sense? Okay, so in this case, well, we know QP is delta H, right? As long as it's only P delta V work. So we're okay there. And so which is bigger here? Delta U or delta H? Delta U. If you did this in a bomb, you'd have to pay more work, right, than doing it under constant pressure. Delta U is equal to delta H plus W. We can calculate. W calculations are pretty straightforward. All right, one last scenario for endothermic. Endothermic like this is where the volume had to increase. So V initial to V final. So here we got our delta U is equal to Q plus W. We're doing this under constant pressure, so it's QP. work is done because the volume changed, V initial is smaller than V final, so in other words, we have to blow up, the system has to blow up the balloon. And so the system does work. When the system does work, does it gain energy or lose energy? System lost energy doing work. And therefore the net energy, QP, is going to be this, the QP, which is equal to delta H. And so even though, if you did this in a bomb, you wouldn't have to blow up against the surroundings. The surroundings is trying to push you. But if you do this under constant pressure conditions, then the system has to blow up the balloon. So not only do we have to do this internal energy change, we also have to push the surroundings to make room. And to push the surroundings out to make room is going to cost us an extra 100. And so rather than 3,000, let's say this normally costs 3,000, this is going to cost us 3,100 kilojoules because of that extra 100 kilojoules blowing up the system's volume. All right, so these are internal energy. Now, what you have to do is you have to understand these symbols so well that you can easily switch from U to H. And so we got to be able to mentally flip. And the only way you can mentally flip, and this is, I told you I was watching those memory videos. The memory videos, the people who get it in the short term, they can't manipulate that, Let's say if somebody just told you a sequence of numbers, right, and you're just trying to memorize that sequence of numbers, and then they ask you, okay, what is it backwards, What is it, what's the middle out to the right, middle out to the left, Can you do all those manipulations in your mind? They say, no, you can't unless it's in your long-term memory. And so the people who die in thermodynamics is they never get the basics in their long-term memory, and they struggle. And so this stuff is not difficult. All you have to do is make sure you get it into your long-term so you can flip your mental switch and immediately switch to enthalpy diagrams. If we switch to enthalpy diagrams, that is, now I'm going to plot H instead of U. Right? If I plot H, well, U is total energy, so what is H then? Is H partial energy? What is H? And so here I'm going to have something called H initial and H final. Let's go with exothermic here. And so H initial, H final. I know that delta H is just equal to H final minus H initial. And so let me do a quick aside here to talk about something. Let's say U initials here, U finals here, and we have a delta U. Can I calculate what my U final is and what my U initial is? What is the number scale here? In other words, what is my reference point? What has the lowest possible energy? What has the highest possible energy? Can you tell me? What is the absolute zero of internal energy? Nothing? I mean, is that it? And so we run into this problem.
The same type of problem we have with the redox chart over there. Let's show the redox chart. The problem with the redox chart is this.
When I go to the redox chart, is the absolute top oxidizer, what is the top oxidizer on this chart? Fluorine. It doesn't get any bigger than that. And then the absolute bottom of oxidizers is Li+. And so should I call lithium plus the 0 point of oxidizer, the worst oxidizer you can have? Is there an oxidizer worse than lithium plus? Actually, there are a lot of oxidizers worse than lithium plus. Like, for example, methane. Is methane a good oxidizer? No, methane's a powerful reducer. Does methane want to oxidize anything? No. And so isn't methane worse than lithium plus? Yes, so surely methane must be the absolute 0 of oxidizers, right? Surely methane is the worst, the absolute worst oxidizer in the universe. Yes? In the universe, yeah, in the universe. Yes? Can you find that absolute 0 of oxidizers for me and tell me? Because, I want my numbering scale to be perfect. I don't like this arbitrary number system that they came up with here. I want something more perfect where the 0 means absolute 0. Somebody came up with this arbitrary system like Celsius, The zeros, you're kind of meaningless in Celsius because the 0 is just some arbitrary point in the middle. I don't want some arbitrary point in the middle. I want the bottom. So I want the Kelvin style, right? Where 0 means something. Are you going to find it? Well, this is a great project for you guys. After graduating, you can devote your life to finding the absolute 0 of oxidizers. Yeah, that would be like Sisyphus type task, right? No, absolutely, because you'll never find. Are you going to find it?
Yeah.
If you do, then somebody else is going to find something worse. Maybe. Are you going to devote your life to such a ridiculous task? Would you? No. And what is the absolute best oxidizer? Is it really fluorine? Is there nothing more powerful than fluorine? No. And so this comes up to the question, what is the 0 internal energy? We know what internal energy is. Internal energy is simple. Tell me what internal energy is. You guys have probably been studying for yesterday's exam, right? So you haven't started reviewing this, but internal energy is potential energy plus kinetic energy. That's it. The kinetic energy is easy, very easy to calculate, but the potential energy isn't. I asked this question before. What is the potential energy of 50 milliliters of water sitting in a beaker at 298 Kelvin? Well, 298 Kelvin, we could get this. But what is the potential energy? Is it 0? It's just sitting there? Or does it have potential energy? It has potential energy, so how much potential energy is it? Is that an easy thing to determine? Absolutely not. And so this term is estimated. Well, there's hydrogen bonding interactions, we got to break those, right? Dispersion interactions, we got to break those. There's energy in the bonds, we got to break those. There's energy in the electrons being held to the nucleus, we can break those. And then the nucleus, we need to start breaking that apart into protons and neutrons. And then the protons, we got to break those down into even smaller particles, right? Where does it end? Well, and who knows? Maybe you could dedicate your life to that, figuring out how small these particles, how much further they can be broken down, right? But this term, do you think it's an easy calculation? This is an easy calc.
Is this an easy calculation?
No.
No, very difficult. You know, people have estimated it, but do you think those estimates are accurate? No. No. So, but not accurate. There's certain things you can say, well, certain things don't change, you know, in potential energy, like the nucleus. Do we break apart the nucleus? No, so maybe we'll have an arbitrary reference point, you know, not an absolute reference point, and do some calculations that way. And so when you have this, there is no number scale. Is there a number scale that we write here, 0 to 1,000,000 or something? No. Okay, what about delta U? Even though, you know, delta U is equal to U final minus U initial, do we ever calculate delta U from internal energy changes? No. We always calculate delta U from the first law of thermodynamics. The first law of thermodynamics says that the energy lost or gained by the system,
Lost or gained to the surroundings.
yes, so it's Q plus W. Well, here we have the same issue. What is enthalpy? Enthalpy is the energy, the gross, right? Recall this, delta H is equal to delta U, what? Okay, this is the gross minus the tax or bonus or whatever else. The sign will change, right? Now, what type of work are we restricting ourselves to? We're restricting ourselves to P delta V work. And so this is delta U plus P external because it's minus P delta V. Delta V is the system. And so P external doesn't change. So this is going to be U initial plus P external times V initial. And H final is going to be the total energy, U final, plus P external, V final. And so what enthalpy is this is the total energy taking into account the surrounding state, you know, the given state of the surroundings so that we can see, or the system, so that we can see how this total energy of the system interacts with the surroundings. And so we get the PV state, PV state. Does that make sense? Why we have the PV state? So that we can see if the system's PV state changes, therefore the surroundings PV state changes, and there's going to be energy exchange there. Versus just totally ignoring the surroundings, you know, and then the energy would be this, right? We could totally ignore the surroundings by doing this in a bomb. Like, I mean, as far as the work goes here. I shouldn't say totally ignore because, well, anyway, so we have this. All right, and so we want to start thinking in terms of enthalpy because which is more useful? Is it more useful for you in your bank account to know your gross pay, or is it more useful to know your net pay?
Right.
Yeah, or your, you know, how much you have to pay out gross, or how much you have to pay, I mean, not pay, you know, pay in, pay out, whatever. Anyway, H is more useful for us, right? And so we want to understand things in terms of H and be able to relate those to U. And so let's take a look at enthalpy diagrams. Right now, quickly. And so let's go exothermic and let's look at some scenarios here. H. H is basically the total energy, right? Taking into account the PV state. And so let's go exothermic, meaning, let's say here's V initial, here's V final. Let's say V initial is equal to V final. And then we have a delta H here. What is delta H equal to? Delta H is equal to Remember, this is your net. Your net is equal to delta U, your gross minus the work. So how much work was done in this? None. And so in this case, delta H is equal to delta U. These are the exact same scenarios we looked at before. I mean, could you flip them in your head? Or is it best to write them out? Probably best to write them out, and then you can just see what we're going to do here. Okay, what was the next one? The volume contracted, right? And so V initial is bigger than V final here. If we're dealing with delta H, then automatically we know that we're dealing under conditions of constant pressure or constant volume? Constant pressure. So whenever we're dealing with delta H, then I know it's constant pressure. I'm in the constant pressure universe. And so here, delta H is equal to delta U plus W. So what happened here? So what is delta U and what is W? In other words, did the system do work or did the surroundings do work? Well, now I'm dealing with delta H, so if the surrounding does work, is it still the system gains energy by having the surroundings do work, or is it different? It's the same, right? And so the surroundings does work, and the system benefits from it. And so now I have a nice little, what we call a tax, nice little tax, or a nice little bonus? Nice little bonus. And so in this case, delta H is greater than delta U. Okay? Remember, delta H is equal to delta U plus W. All right. Here's our V initial. Here's our V final. This is our enthalpy diagram again. Here's our delta H.
How can we code those both of things as a delta H?
Good question. Good catch. I can't call both of them. I have it backwards there. Delta H is not greater.
Isn't delta U greater?
Delta U is greater. Delta U is greater. So, who did the work? The surroundings does the work. And so that means that the system gains energy doing the work, right? And therefore, it gets a little bonus. But if it gets a little bonus, there's something wrong here. Because if this is my net and this is my gross, then shouldn't the net be bigger than the gross? So why don't you take a look and then try to figure this out? Because this is the same scenario I had before. V initial, V final. Did I get the same result in the previous? Look at your internal energy diagram. And the internal energy diagram should match what we say that's happening in the enthalpy diagram. Is it matching?
Yeah.
Shouldn't it be delta U minus work?
The delta U greater than delta H.
Right. Should be delta U minus the work, right? Because delta U is equal to Q plus W, and so delta H is equal to delta U minus W, right? Right, and so even though the system should, what did I say? The system should gain energy because of the maybe he's look. Oh, well, anyway. Do you see how tricky this can become? It's very tricky. This is why people who don't have, who are kind of shaky on it, will always be shaky on it, you know, because you really have to drill this into your long-term memory to be able to work with it. Otherwise, it's so confusing. It's so confusing because, did I do this right? Well, delta H is equal to delta, so this is wrong. Or is it?
No, it's not wrong.
That's right.
You're like subtraction.
Right,
That is right.
No.
No, the system.
That's wrong. It should be.
It's wrong, right? So how can I fix it? You tell me how. You tell me what the best way of fixing it, because weren't the other ones just intuitive? The internal energy diagram, didn't that just kind of work out nicely? Right? And so tell me how to fix this so that you understand it.
I have a question.
Uh-huh.
For experiment 18, the one we're turning in tomorrow, do we have to do the exercises at the bottom?
Yes.
Okay.
The equations you're talking about? Yeah.
Yeah.
Yeah, the reactions.
Okay.
So how can I fix this? Because do you see these two don't match, and they got to match because it's the same reaction under constant pressure conditions. And so they aren't matching, there's a problem. And so I need to fix it. I need to fix this one. I don't want to touch the other one because the other one is intuitive. The system gains energy when the surroundings doesn't work.
It does match. It does match.
Oh, it does match?
Now it does. It doesn't. It's delta U. The other one is delta U equals delta H plus W.
No, I'm saying this. Delta, which one's bigger, delta H or delta U?
Delta H.
I expected to get a bonus. I'm the one who's getting the net pay here. Why am I getting less than my gross pay? If I'm expecting, my gross pay is $3,000, I'm expecting $100 bonus, right? Now I'm getting $2,900? Is that right? No, I'm supposed to be getting a bonus because the surroundings did the work and the system should gain energy. And so something is wrong. And so help me fix it. Help me fix it so that it makes complete sense to you. Because this is, there are different styles of learning. Some people just, don't tell me how to fix it, just tell me what to memorize, right? That's, a lot of people do that, but maybe that's okay. It'll get you through. But this one, you want to kind of intuitively understand if possible. You can go ahead and memorize it because you'll do okay. That's a lot better than just forgetting the whole thing,
I got an idea.
You got an idea?
Because you get energy from the surrounding, system gives energy, but because the sign delta U minus W, because of the minus sign, you're adding the energy in backwards, then you therefore the arrow for W will be downwards from the initial.
Okay. Right. This is the crazy thing about this. The crazy thing about this is this. Minus W. Does that mean the work is negative? That is, we lost energy? No, this negative just means to change the sign on whatever the work is. If the work is positive, then we change it to a negative, right? If the work is negative, then we change it to a positive. And so this negative just means change the sign. it doesn't mean that we lose energy in the form of work. And so if we recognize that this negative is just to change the sign so that this, we conserve energy here, that it works out, then we need to change the sign of the work. I know that the system gains energy. I know the work is going to be, this is what we need to do. Work is greater than 0, right? Versus work is plus W. Plus W just means leave the sign as is, right? But greater than 0 means that the work is actually positive. And so the work is actually positive, then we got to change the sign of the work because, rather than adding the work now, we're subtracting the work, right? And so that means this is wrong. This needs to be inverted. And so, let's carry on over here. This needs to be inverted, so this is a minus W. We had to flip the sign of the work. We know the work is positive. We flip the sign of the work to make it W. And now, that's our delta U. And so now does it make sense? Delta H, we're going to get more energy than our gross. Does that make sense? Now you have to study these two diagrams carefully because it's a lot easier thinking in terms of gross minus a tax or plus a bonus. This is you're looking at your net and what happened. Let's say you netted, I just netted 3,100. Well, how much of that is gross? How much of that is tax or bonus? Okay. And so, anyway, this is why it's so difficult for people to flip from enthalpy diagrams to internal energy and internal energy to enthalpy, right? Because once they figured out, oh, that makes sense, then all of a sudden, it doesn't. And you end up getting confused. And so it makes thermodynamics a difficult topic to digest because you really have to drill it in to your head what these are. And so this is why I was saying, the exam is going to be easier without this stuff on it, right? But I didn't mean it's an easy test. Some people misinterpreted that thinking it's supposed to be an easy test. All right, I'll stop here.